Hello everyone, my name is Glenn and I'm here today to demonstrate the Qubit Factory. So this is an engineering style puzzle game about quantum computing. So myself, I'm currently a research scientist working as part of a team to build an actual quantum computer, and I made the Qubit Factory as a side project with the hope that it could be a fun way for people to learn about quantum computing, especially those without any prior background knowledge in this area. Alright, let's get started. So we'll just skip over the intro dialogue. So this game has several tutorial levels and whatnot to explain the controls and the mechanics, but today we're going to look ahead and go to something more interesting right away. Okay, so this is how a typical level begins. We have an input stream of bits on the left, and we have a logical task we need to perform on these bits. Okay, so on this level, we need to output a 0 if a bit in the stream matches the bit that preceded it, else we output a 1. Okay, so it's our job to build a factory that satisfies this task. On the right hand side, we see the expected outputs if we do correctly satisfy this task. Okay, so I'm going to begin by placing an inversion gate. Okay, so what this does is flips zeros to ones and ones to zeros. So this is not a correct solution, but let's just see what happens anyway. So we start the factory, bits begin to move, they interact with this gate and get flipped as we expect. Then they proceed to the output where they get compared against the expected outputs. Okay, so green means it's correct, red means it's a failure. Okay, so just through sheer luck we get some of the outputs correct, but we still get a lot of failures as well. And if we speed this up, we see that we fail the level. Okay, so how can we compare two bits together? Well, in order to do this, we use a control. Okay, so the function of this is it takes in a control bit and it alters the target gate depending on the state of the control. So if the control is in the 1 state, the target gate acts as usual. If the control is in the 0 state, then the target gate does nothing. Okay, so this combination of a controlled inversion, for those of you familiar with Boolean logic will recognize this as implementing an XOR gate. Okay, so let's proceed. What I'm going to do is just create a single 0 bit just to initialize my control, and let's see what happens. So the 0 comes in, it initializes the control, the first bit gets compared against the 0 and gets output. Okay, so that's looking good. What we need to do though is set it up so the second bit now gets compared against the first, and how we do this is we introduce a splitter to split off a bit before it gets compared, and then we merge it back in to prime the control gate. Okay, so first bit comes in, it gets split, it gets compared, and the split value is used to prime the control gate for the sequential bit. Okay, so now we can see that we are indeed matching the expected output. Everything is looking good. So we can speed this up. And there we go, level successful. So let's preview a more challenging level. Alright, so in this level, we're given 2 input streams, each of 4 bits, and these we're told represent an integer in the range of 0 to 15. Okay, so we have to multiply these 2 integers together and output the result as an 8-bit integer. Okay, so this is a much more challenging task. So here is a solution that I prepared earlier, and we'll just let this run. And I certainly won't try and explain what's going on here because I barely remember myself. But this is just to show you that it is possible to solve relatively challenging computational tasks just using this small set of very basic components. And in fact, the set of gates that we have here is universal, which means that any task a regular computer could do could also be expressed in terms of these very simple control and inversion gates. Although you'd probably have a very difficult time programming something like Doom via these gates, in principle it would still be possible. So everything we've seen thus far has just involved regular or classical bits. Let's move on to see what a quantum level looks like. Okay, so we have a similar setup to what we saw before with a bunch of inputs on the left. However, these inputs now look very different. Okay, so these are quantum bits or qubits rather than regular bits. So what is a qubit? Well, that is the million-dollar question, isn't it? But you'll learn more about this as you progress through the game. For now, qubits are just arrows on the disk. Okay, in this level, we are given a set of fixed gates that act on these qubits, and it's our task to undo the transformations that these gates do. Okay, so let's see what happens. Qubits come in, they get rotated, they get flipped, they get rotated again. Okay, so our two basic gates that act on qubits are these ones that flip across an axis, and these other gates that rotate our qubits by a certain amount. Okay, so looking at the sequence of operations, the last thing that's done is a rotation, so this should be the first thing that I try to undo. And we know that any rotation can be undone by an equal rotation in the opposite direction. Okay, so that's what I'm going to do, is rotate by an eighth of a turn in the opposite direction. The second to last thing that was done on the qubit was a flip, and we should know that if I flip anything twice, I get back to the starting state, or equivalently, if I mirror something twice, it gets back to the original. So I'll place the same flip, and I should undo the first rotation again by doing an equal rotation in the opposite direction. Okay, let's check if this works. So qubits come in, rotated, flipped, rotated back, flipped again, rotated back. Okay, and now you can see that our outputs are matching the expected outputs, so everything is succeeding. So let me just do the same thing on the bottom rail. So rotation in the opposite direction, flip about the same axis, and finally rotation, in the opposite direction. And this looks like it's all working. Everything's going good. And we've actually learned something very fundamental about quantum computing, is that all of the gates we're applying are reversible, which is not generally true with classical computing. So let's just let this run. And there we go. We pass our first quantum level. So I hope that this brief introduction has been enough to give you an idea of what the Qubit Factory is about. Okay, so you have a selection of levels that involve classical computation, regular bits and logic gates. We have a selection of levels that involve quantum computation, i.e. qubits and quantum gates. And as you progress through these levels, you'll be learning actual principles of both classical and quantum computing, and you'll begin to understand the differences between these two types of computing. Okay? And the final set of levels require both classical and quantum computing put together in order to solve, and these cover many important algorithms and protocols used in real-life quantum computing. So let's finish with a little preview of what one of these levels looks like. Okay, so things are much more complicated. Again, here is a factory I prepared earlier, and we'll just let this run for a little bit. So thank you for your attention. The Qubit Factory is free to play from the link in the description, so please check it out.